Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today's topic, extreme values and saddle points on a graph. But first, I want to make a clarification from the previous lecture. So if you recall, the last lecture ended with this linear approximation, something like y to the sixth plus e to the xy, and I wanted to find the linear approximation at the point 1, 0. Well, we found it. So L of xy ended up being 1 plus y e to the xy evaluated at 1, 0 times x minus 1 plus 6y to the fifth plus x e to the xy evaluated at 1, 0 times y. So that was a linear approximation. Nothing wrong with that. Everything checked out fine. You plugged in your points, and you got 1 plus y out of all of that. And so then I said, okay, well, that's fine. Everything's good there. So then we tried to approximate the point 1.1 and 0.1. Here's where the error came. So in the calculator, I plugged in, I reversed this point in the calculator. And so I plugged in 0, 1 as opposed to 1, 0. In fact, the value at 1.1 is approximately 1.16, okay? And from our linear approximation, L of 1.1, 01 gave us an approximation of 1.1. Well, that's pretty good. It's only off by 600ths. So again, this is a calculator error. It actually wasn't my fault this time. So the linear approximation is pretty darn good. We're off by 600ths here. Okay? So that clarifies that problem from last time. Everything is right with this linear approximation. Okay, so on to new material. Extreme values and saddle points. All right. So let's get down to business here. Okay, so if we had a function y equals f of x, and we wanted to find local extrema, right? Local values where you had a max or a min, local extrema. Let's see here. So you looked for points where f prime of x was equal to 0, and that was points where the tangent line was horizontal, right? Horizontal tangent line. Well, in the case of a function of two variables, well, you don't want a horizontal tangent line. You want a horizontal tangent plane, right? You want a plane that is parallel to the xy plane. It's horizontal, okay? So to find local extrema on z equals f of xy, you look for points where partial f, partial x is 0, and partial f, partial y is 0, right? And that will give you a horizontal tangent plane, right? So where both the partials are 0 is a horizontal tangent plane. Okay, a plane that is parallel to the x-axis, right? Okay, so where am I here? Okay, the local maxima and minima, well, just like in a function of a single variable, they're just the highest points in the neighborhood, right? They're the highest points in the neighborhood. The highest points around. They may be the highest points on a particular surface, but they are the highest points to an individual area of a graph. So as an example, let me get rid of all this. All right. So we will get rid of all this. And then if I did something like a paraboloid, like that, right? And I had it sitting on the xy. There's z. So the paraboloid has local min of 0 at the point 0, 0, right? It actually ends up being the absolute min. It's also a local min. It's the lowest point around, right? Lowest point in the paraboloid around. And then suppose that's something like looks like this. So I had a surface. So how to make this look mildly 3D looking. So some kind of surface, and then maybe it's kind of drooping down like that and looking like kind of like a board like that, right? And then in the middle of it, so I should probably get rid of part of that, and then maybe it's got sort of like a hump like that, right? And maybe the axes, maybe they sit like there, right? And then, so there's x, there's y, and there's z. And suppose this point up here is, I don't know, 1/2, comma 1, comma 5, right? So this surface has a local max of 5 at, say, the point 1/2, comma 1, right? And that may be the absolute max. We don't know, but I mean, it is going to be the local max. Maybe this thing has other maxes over here that are higher than it. We just don't see them in this picture, but that's a local max, certainly, the highest point around. Okay, so how do we find the coordinates of local extrema? Well, just like when we had a function of one variable, we have tests involving the derivative, all right? So we have the first derivative test for local extrema, all right? And what it says is this. It says if a function of two variables, f of x, y, has a local max slash min at an interior point, AB of its domain, right? And both the first order partials exist, f of x, y, fy, AB exist. So you have a local max or min, both your first order partials exist, then the consequence is that the first order partials are both 0. And the tangent plane is horizontal. It's worth noting, too, that these being 0, think about the equation of a plane. It involves the partials being the normal vector there. So that's why those 0 out in your equation. Your plane is just z equals some constant, so it's horizontal. That's the reason why this implies a horizontal tangent plane. But this is saying that if you have a max or min and your partial both exist, then they are both 0. So the result here is that at local extrema, the tangent plane is horizontal if it exists. Now remember, sometimes we have these weird functions that are not differentiable at certain points. They have kind of funkiness going on. But if it exists there, it's horizontal. However, what is not true is the converse. So the converse is not true. That is to say, just because your partials are both 0 does not mean that your point is a local extremum. So if the first order partials are both 0, it's not necessarily the case, AB not necessarily a local extremum, right? It could be something else. Just like when we had situations in calculus of a single variable where you had inflection points going on, right? They had first-order partials or first-order derivatives being 0, but the point wasn't necessarily a local max or local min, like, for example, on x cubed. Right? It had an inflection point at 0. A similar kind of thing exists here. So, okay, definition. Well, critical points were points where f prime was 0 in the single variable case. It's essentially the same definition for the multivariable case. So, definition, an interior point, AB. And I'm just saying interior point because I'm kind of distinguishing that from a boundary point. We can have extremums at boundary points, and they're kind of different. So, interior point of a function f of xy, where the first order partials are both 0 at a, or one or both do not exist is a critical point. So, same definition more or less. Either the first order partials are both 0 or one of them or both of them doesn't exist. That's essentially the same definition for single variable calc, except we only had one derivative then. So the first order derivative was 0 or it didn't exist. That's a critical point. Right? And the fact is, f of xy can only assume its extreme values at critical points or boundary points of a closed domain. Okay? So, for a single variable function, like I said before, right? A critical point sometimes meant a local extremum, and sometimes it meant an inflection point. All right? Something very similar is going on here. All right? And we'll use the new eraser. So, okay. So, let's see here. So, for a function of two variables, there aren't really inflection points because there's no change in curvature, or there's no change in concavity of a curve, but you can either have local extrema or you can have what's called a saddle point. Right? So these are points that act like a local max in one direction and a local min in the other, right? So saddle points are points that act like a local max going in one direction and a local min, I should say in another, not in the other. There are lots of other directions out there. In another, right? So think back to our talk about hyperbolic paraboloids, and let me redraw one up here. So e.g., let's see here if this is going to look decent. Probably. All right, so that'll look something like that maybe, and then how about that? Okay, hyperbolic paraboloid, sure. So it had a saddle shape, and this is called a saddle point for that reason. I mean, so look at this here. So clearly, if we're walking in this direction, right? Or from the other side, you can't see it here, but if either direction here, this is a local max. It's the highest point around, right? But if we're walking in that direction, so this is a max, it's a minimum. It's the lowest point around, right? So saddle point, aptly named. This is a saddle-shaped curve, right? So this is, remember, this is a hyperbolic paraboloid. Okay, has a saddle point. Okay, let's do an example here, and let's use the first derivative test. So let's get rid of this. Okay. So, example, let's find any local extrema of f of xy equals 3x squared plus y squared. All right, well, that's a paraboloid, so it should have a local extrema, it should have a local min. Right? So first of all, there are no boundary points to consider here. Right? So this thing has domain all real numbers. So the only possibility for local extrema are critical points. Right? So if there are any local extrema, they're going to come from critical points of this function. So partial f partial x of this is just what, 6x. Partial f partial y is just 2y. And when these two are simultaneously 0, that's a critical point. So critical point occur when these are simultaneously 0. Well, that clearly occurs only at the origin, right? Only at 0, 0. So no other point will make them even 0, period. So that's the only critical point. Okay. And so we know this is a paraboloid, it opens upward, and so f of xy is going to be bigger than or equal to 0 at every point, right? F of 0, 0 is equal to 0. So 0 at the point 0, 0 is, well, I'm sort of being a little bit abusive with my language here, but so 0, 0 is a local minimum. And in fact, this is the absolute minimum of the function. It's the lowest the function goes, but for us right now, local minimum is fine. Absolute mins are always local mins too, not vice versa, but this is definitely the case. Okay, so there's one local extreme, it's 0, 0, it's a local minimum. Okay, now, let's try another one here. Okay, so let's find the critical points of f of xy equals 3x squared minus y squared. Okay, well, again, critical points are where you have the first order partials simultaneously 0. So again, here 0, 0 is the only critical point. Well, now the question is this a local max? Is it a local min? Or is it a saddle point? All right, well, let's take a look at it. So if you approach the point 0, 0, also it's worth noting up here that f of 0, 0 is certainly 0, right? So as you approach 0, 0 along the positive x-axis, well, what do you have? You have points that look like x comma 0, right? So you're walking along the x-axis, every point has this coordinate, x comma 0, and the x's are positive. Okay? Yeah, so when I plug that point into my function here, I get just 3x squared, right? Because the y part goes away, y is 0, you know, okay? And so this is definitely going to be greater than or equal to 0. In fact, it's going to be strictly, yeah, greater than or equal to 0 for all points on the approach path. All right, so as you walk along the positive x-axis, right, this is going to be, so these function values are going to be greater than the function value here, right? This is a function value of 0. These function values are going to be greater than that. So what I want to say here, so travel along the positive x-axis, all right? 0, 0 is a local min, correct? Because every point you're always higher up than 0, and eventually you get down to 0, 0, and you get to 0. So you're at a local min there. All right? Well, now let's approach along a different path. Approach 0, 0 along the positive y-axis. And we have points of the form 0, comma y, where y is positive, all right? Okay, so f of 0y gives you what? Negative y squared. Well, this is always going to be less than or equal to 0 because it's negative, right? For all points on the approach path. And so if you travel along the positive y-axis, you're always going to be less than 0, so 0 is the high point. 0 is a local max, right? So you travel along that, 0 is a local max. Well, if something acts like a local min at some points and a local max at other points, it must be a saddle point, right? So therefore, 0, 0 is a saddle point, right? Saddle point. Well, the only possibility for local extrema were at critical points or boundary points. No boundary points here to find everywhere. The critical point, the only one, resulted in a saddle point. So consequently, there are no local extrema. Right? This thing has no local maxes or mins. It only has a saddle point at the origin. Okay, well, sometimes this kind of analysis is a little bit trickier than I've made it seem here. It's hard to find good approach paths, and sometimes it's hard to figure out if local max or local min, right? So instead, we have a test. And just like we had a test on the second derivative for concavity in single variable calculus, we have a second derivative test for local maxes and local mins here in saddle points. So the second derivative test for local extrema. And this will identify not only a local extrema, but also what kind it is. Okay? So you're assuming that f of xy is continuous, and the first and second order partials, second order partials are also continuous. Around the point AB, right? And you're assuming here that you have a critical point of the variety that the first order partials are equal to 0, right? So you're at a critical point, and now your question is, well, what's happening with that critical point here? Is it a local max, local min, or saddle point, right? Okay, well, here's the test. So I should say then the following results hold, okay? F has a local max at AB if what? If the second order partial in the x direction, f double x, is less than 0, and this crazy quantity, f double x, f double y minus f xy squared is greater than 0. Okay, at AB. So we'll get back to that shortly, but so this second order partial is less than 0, and this funky quantity here is bigger than 0. That's a local max. Okay, well, you have a local min if, let's see here, this time fxx is greater than 0, and this funky quantity is still greater than 0 at AB. So this thing is still bigger than 0. Now your second order partial x is also bigger than 0. Okay? Well, f has a saddle point if this quantity over here is negative. fxx plus fyy minus fxy squared is less than 0. Okay? And the test is inconclusive if that big quantity ends up equaling 0. Right? Test is inconclusive there. And these are both at, this is at AB, and this is at AB, right? So these are all at the point. Okay? So there's the test. Oh, look at that. Okay, note over here, well, this quantity, you know, you could think of this as a determinant, actually, in the following way. So what is it? It's fxx, fyy goes down there, fxy, fxy, right? This determinant is this quantity here, isn't it? Yeah. So fxx, fyy minus fxy squared. This is called the Hessian of f. Okay, and it's called the Hessian of f. Okay, so what does the test mean? Okay, let me erase. Let's talk about the Hessian for a minute and its behavior. Okay, so if the Hessian is positive, at a point AB, then what does that mean? It means that the surface curves the same way in all directions at AB, right? So it means that the surface is curving at some point AB in all directions out of it. The surface is curving, so it's either curving up or it's curving down, right? So it's either curving up like this in all directions, or it's curving down, right? Curving down like that, okay? And in particular, it's downward if f double x is less than 0. Therefore, AB is a local max. And it's curving upward if the change in double x, or f double x, is less than 0, and therefore AB is a local min, right? And if the Hessian is negative at a point, if Hessian is negative at a point, right? Then what? Then, oh yeah, sure. So then the surface curves upward in some directions and downward in others. And thus, AB is a saddle point. And this is certainly proved at higher level tech. We're not going to do anything about proving it here, but this is the way the second derivative test works. Okay, it talks about the curvature of a surface, what direction it goes in at a point. All right, let's try this out here. So let's get rid of this. So let's find any local extrema of what function? Let's use xy minus 2y squared plus x plus 2. Okay? So there are no boundary points. The derivatives exist everywhere. So there's no possibility of having the partials not existing. So therefore, the only possibility for extrema, critical points. So the only possibility for extrema, critical points. Okay? So, all right, partial f, partial x. Okay, that ends up being what? Y and plus 1? Yes. Partial f, partial y ends up being x minus 4y. Yeah, okay? And these two must be simultaneously 0. So, must be simultaneously 0. So, okay, well, the first one's easy. Y plus 1 equals 0 implies that y must be negative 1. Plug that in over here. So x minus 4y equals 0. X minus 4 times negative 1 equals 0. X plus 4 equals 0. So x must be negative 4. All right? So the point negative 4, negative 1 is the only critical point. All right? Okay? It's the only critical point. All right, well, let's check the Hessian then. F double x is just 0. Right? We don't even really need f double y, but it ends up being minus 4. And then f of xy, that's f of y, that f of x of that gives you 1. Is that right? Yeah. Okay. So the Hessian, remember, it's f of xx, fyy minus f of xy squared. That's 0 minus 1. That's minus 1. The Hessian is negative as a consequence. So Hessian less than 0. Therefore, negative 4, negative 1 is a saddle point. Right? Consequently, the only possibility for local extrema was at this point, at the critical point. Therefore, here f also has no local extrema. Okay? All right. So, last topic of this section, absolute maxes and mins. I said earlier that it's definitely true that an absolute max and an absolute min are local max and local mins, but the converse is not true. Same applies of the single variable case. You may have lots of local maxes and local mins, and there's only one absolute max and one absolute min. But it may occur at more than one point. That's possible. So, all right. Absolute max slash min on a closed, bounded region of the plane. There's a mouthful. All right. Okay. So, how do you get it? Well, you find the critical points of the functions of the function on the interior of the region. Right? So these are possibilities for local extrema. They may not be local extrema. I don't know. Doesn't matter really, but you find them and then evaluate f at these points. The whole idea here is you're making a list of all the possible values that could be the absolute max and min, and then when you have that list of all the possible values, you go through and say, okay, which one's biggest, which one's smallest? Pluck them out from that list. That's the idea here. So these are possible candidates. Okay. What else is a possible candidate? So I guess the next step would be evaluate f at points, or let me say it this way, at n points of the boundary, right? So if your boundary is some polygonal shape, there's going to be endpoints. You can always check those. If it's a circle, there's no endpoints, but we can live with that. So if there are any endpoints here, you could check those, because we know from calculus of a single variable that a function can achieve an extreme value on a boundary point, right? It can do that, okay? And you also have to find the critical points of the function along the boundary, right? Okay? And then evaluate those. So that's the one thing we haven't done yet, is finding those critical points along the boundary. We'll do that in a second with an example. And then pluck largest, smallest f values from the list of candidates. That's an n. All right, so these are all your candidates, these interior critical points, these boundary endpoints, critical points along the boundary, whatever is the biggest and smallest, absolute max and absolute min. Okay, let's try one. These can get a little involved depending on how involved your boundary is. Let's use a triangle. So, okay. Let's find absolute max min values for f of xy equals 2 plus 2x plus 2y minus x squared minus y squared on the triangle bounded by the lines x equals 0, y equals 0, and what do I have here? Y equals 9 minus x. Right, so we got 3 lines for a triangle. That works. So our boundary region, there's 9, 0. There's 0, 9. There's 0, 0. There's our boundary region. We care about what is the function's absolute max, absolute min on x, y points in that boundary region. Okay, first things first. Interior critical points. Well, that just means looking at partials and finding them equal to 0. So, first order partial with respect to x is 2 minus 2x. With respect to y, it is also 2 minus 2y. Right? Those need to be simultaneously 0, so 2 minus 2x equals 0 implies that x is equal to 1. Is that right? The 2 over, and does everything look good there? Yeah. And then 2 minus 2y is equal to 0 implies also that y is 1. Okay? So 1, 1 is an interior point. There's 1, 1. That's a possible candidate. So over here, I'll list the candidates. So the points 1, 1, and their function values, f of 1, 1, if I plug in 1 to this function, I get 2 plus 2 is 4, plus 2 is 6, minus 1 is 5, minus 1 is 4. So their value, so their f value is 4. So that's the value of f at that point. Okay? And that's the only interior critical point that there is, 1, 1. Okay, the boundary points. So now boundary. How do I want to do this here? Yeah, okay, we can do it segment by segment. All right, so there are 3 segments here, 3 lines. I'll take each one separately. So we'll start along the horizontal segment. So the segment from 0, 0 to 9, 0. Right? And you could certainly check the endpoints first and then do the boundary critical points. I may as well do it all in one fell swoop. So I'm going to kind of combine those 2 steps into one step here. Okay, so at every point, am I doing the right thing here? Yeah, okay, this is right. So at every point along here, the y value is 0. Okay? So what your function started off as f of x, y equals some junk. But now, if y is always 0, you're left with just a function of f of x, right? So you've got 2 plus 2x minus x squared. This is just a function of x, right? Because the y's are all 0, correct? Okay. So we could check the endpoints into this and see what they yield and get critical points, right? So check the endpoints. So f of 0 gives you, what, 2? And f of 9 gives you 2 plus 18 is 20, minus 81 is a negative 61. Okay, those are the boundary points. Those are boundary points. Okay, so we can actually list those over here if we would like to do that. So we'll list 0, 0 first. Its function value is 2. We'll list 9, 0. 9, 0. Its function value is negative 61. Okay. Now, does this thing have critical points along the boundary? All right. Well, f prime of x is what, 2 minus 2x, right? And so when is this 0? 2 minus 2x equals 0, which implies that x equals 1, right? So the point 1 comma 0 is a critical point along the boundary, right? It's a critical point along the boundary. Therefore, it has to be considered. There could be an extreme value there. So 1 comma 0, if I plug in 1 here, I get 2 plus 2 is 4, minus 1 gives me 3, right? That's what I have, yeah. Okay. So there's one segment. Okay, we're 1/3 of the way done. Let me erase this up here, and we'll go to segment 2. I want to leave my picture up though. So here's an endpoint we cared about. Here's an endpoint, and actually here's a point that was a critical point along the boundary on the segment. All right, let's go now to the vertical segment. So the segment from 0, 0 to 0, 9. Well, we've already checked out 0, 0. No reason to do that again. It's done. So now, everywhere along this segment, x is 0. This becomes a function just of one variable y, right? So what do we get? 2 plus 2y minus y squared. Same function, just with y instead, right? And so if we check out f of 9 here, we do get negative 61. So we can add the point 0, 9 to our list at negative 61. And if we differentiate this with respect to y, we're certainly going to get 2 minus 2y. And so y equals 1. So 0, 1 is a critical point along the boundary, again, just like 1, 0 was. All right, so there's 0, 1. That's a critical point. And it's going to give us the exact same value that 1, 0 did of 3, right? So check this endpoint up here. Check that endpoint. Already did it before. Critical point along the boundary. So now we have, what, 6 candidates, 2 critical points. Three critical points, 2 boundary points. How did I get 6 out of that then? Did I do 1 twice? 1, 2, 3, 4. All right, check this. Okay, so this is already done. Okay, yeah. So there's 3 boundary points, 3 critical points. All right, we're in good shape. Last segment is this diagonal segment here. And the endpoints are already done, both of them. We don't care about that, but there may be critical points in that boundary segment. So this is the segment from 0, 9 to 9, 0, right? And in this case, we can't just zero out one of the variables, but it's a line, so we can replace y with x and get a function just of x, right? So we began with f of xy. Well, that turned into f of x 9 minus x is our new y value, right? That means we have 2 plus 2x plus 2 times 9 minus x squared minus 9 minus x squared. So if you do all that out, what do you get? 2 plus 2x plus 18 minus 2x minus x squared. Let's see, this is a minus x squared and a plus 18x and a minus 81. Okay, combine all that up. The two x's are gone in the middle. That makes a 20, negative 61. Let's see here. So there's a negative 2x squared, and am I seeing a plus 18x minus 81? Is that what I've got? Yes. Minus 61. Yeah, because 2 plus 18 is 20. Yeah, minus 61. That looks better. Okay. So there's our function. Take its derivative. This is just under x. So take this thing's derivative. What do you get? You get 4x plus 18. Right? Let me come back up here again. So you have this thing here. Well, when is it 0? Exactly when x is equal to negative 18 fourths, which is negative 9 halves. Right? So when x is negative 9 halves, y is, wait, is that right? 4x plus, no, this should be negative 4x. Ha, that was better. That should be negative 4x. So this should really be positive 9 halves. Yeah, there we go. Positive 9 halves, right? Let's see here. Yeah, and then so y is 9 minus 9 halves, which is 9 halves. 18 halves minus 9 halves is 9 halves. So the point 9 halves, comma 9 halves, which is smack dab in the middle of this line segment, is a critical point. Okay? And the question is, what is its value? Well, you can plug those in to that function or that function. It doesn't really make a difference. But you plug them in, and you get f of 9 halves, 9 halves. What have I got here? Negative 41 halves, right? So that's our very last candidate. So that's negative 41 halves, right? So we have 7 possible candidates, 3 endpoints, 4 critical points, 1 interior, 3 on the boundary, right? So what's the absolute max and absolute min? Well, absolute max is 4, the biggest value on this list, and it occurs at the interior critical point 1, 1. So this surface is highest at this point, right? And the absolute min, well, it's negative 61, and it occurs at 2 points, 0, 9, and 9, 0. So at these 2 points, this thing has the same height, and it is negative 61. Okay, that's it for extreme values.